Good morning, everyone. I'd like to start with a little, let's say, hopefully not too complicated session on theory about Markov state models, but you get a kind of better picture in your head about what is actually going on. My name is Jan-Hendrik. Feel free to ask questions anytime. The idea is that you understand what's in the talknet, that I finish it, okay? It's supposed to be not too complicated. We'll see if I manage to do that. Okay, let's start with a little introduction about actually why we're using Markov state models, or what the overall picture is. I usually think about it as we're the scientists and we're interested in about how something works, and we want to compute some properties that interest us. I don't know. Like in this peptide systems, we want to know how fast something is docking or it's released, or how strong something binds, or what are the main states that something takes, so that you can design a drug that acts on something. Okay, this of course is very difficult. If it would be easy, you wouldn't be sitting here. So what do? We usually have two choices. Let's say nowadays we have two choices. Say like 30 years ago, people usually always did experiments. We measured something, some observation, and at the end we tried to figure out something out of it. Nowadays we can also make a simulation, right? And that's what we are trying to analyze. So in the end, the idea is not to directly find the properties of interest, but take the detour about making an experiment or simulation, making some estimations so that we have a simplified model, and this allows us finally to compute what we are interested in. Okay, and so PyEMMA is kind of doing this intro for you in a way. So this is the Markov state models that I'll be talking about how to get the simulations and kind of get the data that is used to make the model. That was kind of part of yesterday. I also talk briefly about how to get from the Markov state model to some properties of interest, so that we kind of close this circle in a way. Okay, so yeah, that's what I just said. Okay, MSM. So what are Markov state models? So let's first look at this movie. You're probably familiar with this. I guess I've shown it 100 times. Other people here in the building too. I think that's been originally made by someone in the ZIP building. Actually, I don't really know who, but since I'm working on this, I know this movie. It's very nice because it illustrates a lot of things that are kind of happening. So you have this little peptide that is moving around. And you see there are a lot of atoms, a lot of things are moving all the time, so nothing's like really standing still. But just by looking at the eye, when you have this colored overlaid, it's clear that there are more or less three partially stable configurations. And if the computer would be intelligent, you could just say, okay, this is the movie, and then tell me something about it. It would probably say, okay, yeah, there are like three states, or instead of a computer, you might ask a student and say, okay, what can you figure out just by looking at it? Okay, so just by looking at it, we figure out that this is kind of happening, and so the dynamics that we're interested in have this special behavior that it's kind of metastable. So it's wiggling around, but it looks to have a kind of well-defined structure in a way. We have these three states, and it's jumping from here to here. It's going from every one to every other state. And to describe this picture, you can use what we call the transition probabilities, and say after a certain amount of time, there's a certain chance that the system jumps from one of the states to another one. I mean, it sounds rather trivial, and actually Markov state models is in some way the simplest possible model that you can think of, right? So there are certain states in the system, and over time it can just go from one to the other. There's no other possibility. And all that you write down is saying after a fixed time, what we call like a frame of the recorded points in time, we say there's a certain chance to go from one to the other. So, for example, I made up these numbers, they're not correct. Okay, so this is kind of what a Markov state model is in a nutshell. Now a little theory about how this actually comes from, because I mean, to derive at this kind of discretized very simplified picture, it's kind of a rather long way because we're simulating a protein, probably in water with lots of atoms, like several thousands, and we want to end up with something that is discrete. So how we're going to do that? So let's first introduce the thing that we call kind of the state space, not kind of, what we call the state space. We're saying that each of these configurations, and I'm not talking about the general green one or the general blue one, I'm talking about really a specific set of atomic coordinates. So they're infinitely many because coordinates are continuous. And you can imagine that this is, can be expressed as a point in a very, very high dimensional space. So each of these particular configurations that you see in this, let's say, 2D projection of this very high dimensional space is just a single point. And then the trajectory that you've observed is just, I mean, can be depicted as something that is moving around in this space. It's usually very, very high dimensional, but so when we're talking about a trajectory, then it means actually a path in this really high dimensional space. You see that it has a lot of kinks. This is because we usually record it only at certain intervals in time. Although it is continuous, so usually it will just run smoothly. For us, what we can see on any experiment, you have a certain sample rate. There's nothing that you can really sample something continuous. This is probably what you would have. So this is what we call a path, usually denoted with x of t, or t being the time steps. So this is the state space, just that you get some terminology. And at the end, we want to figure out, from looking at the trajectory, where are these kind of metastable sets, so that we can then, from the trajectory that's been running around, you figure out, okay, this is the kind of more or less self-contained set, this is a self-contained set, and this one. And this is what we call, in a way, metastability. So if the trajectory resides in a region for a very long time and it only occasionally jumps to another region, this region is what we call metastability, just in a kind of very abstract way. I didn't give any like mathematical definitions, but we'll come to that. Okay, I talked about time series, so this is just x of t. So this is kind of, if you want to be correct, it's a realization of a stochastic process in a probability space. These are some mathematical things that you need to have for this probability function that I will explain shortly. All the mathematics that appears, I mean, you'll have the slides, you can look at this later if you want. I'm not going to explain everything that's kind of to make it kind of rigorous, but it's not important right now, just for later if you want to look at it. Okay, so since we have a trajectory, the other thing that we need is we want to cover the whole state space with this probability. And first I introduced the continuous transition probability function. So if you're familiar with the transition matrix from yesterday, this is the continuous version. So instead of saying what is the probability to go from this state to this state, I'm saying what is the probability, differential probability to start at this point and after a certain time, tau reaching another point. Just the probability would be 0 because it's just really from going from a point to a point, the probability is 0. But so this, to be really precise, is you have to say, okay, I'm ending up in a certain region when I start at a certain point with my processor. Just to be realistic. Okay, but this is, you can consider that this thing is a continuous representation of the dynamics. So this is the most general object that can describe your dynamics. If you allow that this tau is completely, so you don't impose any properties on the tau. You just say, okay, I know if my system is in this state, then I can ask what's the probability that I end up in some other place after a certain time tau. So this is still very, very general. And now we're going from this kind of single point idea. So we say that the system is always at a point and moving around. And we're saying now we have like millions and millions of things that are all moving at the same time. And I distribute them at some point, and all of these things are kind of moving. And then if I go from points to really like an infinite number of points in the distribution, then I end up with a density that is kind of moving. think this, I guess intuitively that was probably clear to everyone, but I just want to point out that this is not super trivial to do in reality. So you have like two pictures. You have the picture of a single particle traveling around an infinite amount of time and spending in certain regions. And you can have the picture of like an infinite amount of particles running around for, let's say, a very short time. And they're kind of expressing the same dynamics. So the particle is here moving around a long time. I could just chop this up in lots of little trajectories and kind of interpret as something that I have a distribution of starting points that are moving just a little bit. So this, let's say this is kind of the particle picture, and this is kind of the density picture, if you wish. Okay, one important property of this probability distribution is, of course, that if you integrate over all points in space, it has to add up to 1, because the probability to be somewhere in my whole state space needs to be 1. It can't be anywhere else. Okay, so this, all that I said before, is just general stuff about dynamics. So it doesn't mean that this is Markovian, and we are talking about Markov state models. So it's, of course, important to explain what means Markovian in this context. Because before, I'm going back, so any dynamics can be expressed in this way. So there's no specialty. So what means Markovian? In say very short, I'll say no memory. You've probably heard that thing a lot. So Markov state is kind of memoryless, but what does it mean? If you write it down in a formula, it looks kind of rather lengthy and complicated. Look at this. It means that the chances, if I have been at certain points in time at these places, and I started at x, then the chances of ending up at a certain region A after a time tau does not depend on anything that happened before t. So it's only depending on the current position. So if I want to predict where I will end up in a second, it only depends on where I'm now. It doesn't depend on where I came from. That's kind of complicated. You can imagine that we had this, someone just asked me to open the door here, the other door. So imagine that the chances of me, so one state would be being in this room, and the question is, through which door will I leave? Then the chances, if I can tell you through which door I came in, it's probably the same way that I will go out, right? Because if I just entered through this door, and you're asking, okay, what's the chances that I leave through this door or through this door, then it's probably higher to leave through this door. But if I came through the other door, it's probably more likely to leave the room through this one. So you can imagine that in some dynamics, it matters where I kind of came from, because it's easier to go back in a way. For Markov models, this is explicitly not the case. So it seems like a rather harsh imposement on your dynamics. So if I come into the room, I will first kind of close my eyes, spin around, so that I have no idea I'm wandering around, and so then the chances to exit through one of the doors doesn't matter where I came from. The decision is actually just depending on where I'm now. Okay. Yeah. So this is a Markov property. What is, I guess, good for us is that nature is Markovian, if you wish. So if you look at Newton's law, then it says that the change in velocity or the change in position depends on where I'm now. It doesn't depend on something 2 seconds later. If you look at quantum mechanics, so all the physical laws that you're familiar with, they are, in essence, Markovian. So that means that even though this seems like a very strong assumption to make, it is actually enough to describe nature, and that's, I guess, enough for us. So you can design other dynamics that are more complicated, but if you just want to express Newtonian dynamics or quantum mechanics, that's not a problem. The problem comes in, I'll talk about this later, when we're not asking about the full dynamics, but we're only asking about projections, especially jumping between states and not. So we don't have every information available. Okay, a last thing that I want to mention, because it's, you might hear this, it's the Chapman-Kolmogorov semigroup property. do later. You heard probably the Chapman-Kolmogorov test that we'll do later. And this is very related. It just means that if you look at the probability, the chances of making a jump for like a longer time can be decomposed into two steps. So I'm saying, if the chances to go from here to anywhere and then to this point must be the same probability as if I would do the same thing in the total time directly. It's kind of obvious, right? Otherwise it wouldn't be consistent. So if I'm saying, what is the chances to end up after 2 seconds at a certain place, then it would mean it should be the same probability as doing twice 1 second. Otherwise it's, I mean, the question is which one do I take, right? If they give different probabilities, because making 2 steps of 1 second should be the same as making 1 step of 2 seconds. Okay, and for Markov state models that's true. Yeah, so just mention this because we're kind of testing if this property holds at the end. A few more properties. Please ask if you're, realize that some people are kind of spinning their heads. I mean, keep on talking, I don't want to stop you, but if you have a question, you can also ask. Irreducibility. In the Markov state models, if you see something which is called active state, or the active states, then this is what belongs to this mathematical property. It means that there's a chance to reach any other state in the system in a finite time. So that means we don't have like estimated dynamics where it's impossible to go from one state to another one. If that's the case, so if you can't really go from A to B or from B to A, so there are two dynamics completely discoupled, then you can't build a joint model for these states. Because there's no way to say what's the chances that something's happening here interacting with something that's happening here. So it basically means if this is the case, you need to make two models. There's no way to connect these. So we require for all our models that these are in a certain way connected so that it's possible, not necessarily direct, but within a finite amount of time to reach any state from any other state. Yes, the other important property, and this is where I go back to this picture of like single things moving around and densities moving around. Who of you is a physicist? Okay, those are them. So you might be familiar with this term of ergodicity, and in a short term it means, I mean, to put it very simple, if I make computations about properties by this way, it should be the same as doing it by this way. So it's the same as if I observe one particle for a very long time, or I observe lots of particles for a short time. And if this is the case, it's not necessarily this case, then I say that the system is ergodic. And to make this kind of happen, for a Markov state model, we need to make sure that everything is connected, so all states are accessible. This is connected to the irreducibility. And the other thing that we need is that nothing is cyclic. And if you're wondering what would be a good example, then I can just need to go to the blackboard. So we have the chart here. Didn't check that. Let's make a very simple transition matrix that is kind of cyclic in a way. So if this is a transition matrix, it's totally fine, right? There's a certain probability to jump from one state, but that's kind of the flipping, right? If I'm in state A, I go to B, next step I will go to A. It would ask you, let's make this a little more simple, otherwise we run into a problem. So 4.9, 4.1. So if we're looking at this model, then this is kind of equilibrated, but it's kind of flipping around. So there's kind of a cyclic behavior. And if I would ask you, well, what is the stationary distribution? I think I really need the one. I'm sorry. To make it easier. Then you probably say, okay, if I look at a trajectory, then it will spend 50% of the time in state A and 50% of the time in state B, right? So in this picture, I would get like 50-50% of the states in the distribution. Okay, very simple. Now I'm going to this picture and I say, okay, because it doesn't matter where I start, I put all my particles. Let's say it puts 80% in this state and 20% in this state. Then, after one step, the probabilities will switch. After one state, the probabilities will switch. So one state, probabilities will switch. So the station distribution will always be either 20-80 or 80-20, but never 50-50. So in this simple case, depending on how I initialize my system, this picture, or in a way this picture, will give me a different answer than this one. So that means if I have such a dynamic, then in a way this doesn't obey the no cyclic dynamics. In most cases, you will never have to deal with this because, as I made this mistake, if this is not exactly 1, so if there's a little mixing, then this property is completely destroyed and you don't have any problems. Okay, I just want to make sure that this is not really, so there might be cases where you encounter this thing, so just that you've heard about it. Does it make sense? No? Yes? If you want to ask later a question, okay, please go on. Okay, avidicity. So, last thing that I want to say is this mathematical object which corresponds to the transition matrix is what we call the propagator, and instead of containing the probabilities to go from a certain point of space to another point, this is an object that transports a distribution, or in transition matrix speak, it transports a vector of probabilities. So it says 20% of the particles are here and 80% are here. You can ask 1 second later what will be the probability distribution after this. And in this particular case, it will just flip, but in a normal system, usually this will converge over time to the stationary distribution. So this is the object that transports the distribution P over time in the time step tau to a new distribution. And all it does is kind of making, putting the integral over this transition probabilities with this initial distribution. And in transition matrix speak, this will be the matrix, this will be the initial vector, so it's just a matrix multiplication. So instead of having the integral, you would have a sum. Okay, I will mention a new term that is, so there are a lot of things to learn about Markov state models. One of the, so first, what I said is just Markov state models. There's a special type of Markov state model that we are always using because it's also in a way natural. These are the reversible Markov models. So we're talking about microscopic reversibility or detailed patterns. What does it mean? I wrote it down like this. So it means that the chances of going from state X to state Y weighted with the chance that I'm actually in the dynamics in equilibrium that I would start in this state has the same probability as starting in the end state and trying to go backwards. Yeah, so if you, let's see if I can go back to this picture. So if I'm looking at this thing and it has a certain distribution, so I'm saying that if all of these particles are moving and I'm looking at, I'm just counting how many particles are actually moving from here to this region and from this region to the other region, then the number of particles in this total picture, provided that my distribution of these particles are actually in equilibrium. So this has run over a long time and everything has kind of evened out. And at some point this gets kind of stationary. So this distribution doesn't change anymore. That kind of makes sense, right? So that this will happen eventually. So if I start all my particles here, they will kind of flow to everything and everything is going back. And at some point, this, like the distribution doesn't change anymore. What I haven't said is that, so that this is happening is always happening for a Markov state model that is ergodic and kind of doesn't have these problems. But I haven't said that if you really look at little regions and say, okay, how many particles being in this region will actually travel to this part, and how many of the particles here will travel to this part. And reversibility says these must be the same. Okay, so the picture is not changing not because the global thing is not changing, but because whatever little place I look at, there are as many particles going from here as are going from here to the other side. And then the whole picture doesn't change, right? Because these pictures, they will kind of swap. What doesn't, okay? So that's what it means. So if the distribution is already in this stationary distribution, which I call pi, then kind of the fraction of particles that are moving from x to y are exactly the same fraction of particles of the total ones that are moving from y to x. So now, why is that important? If that would not be the case, you could imagine that some particles, or there's kind of flow of particles in the system. So they're moving from here to here, so it's easier to take this way than take it another way. And in kind of physical terms, that would mean I could design a machine that takes advantage of this, and I can kind of make a little motor or something that is just driven by this imbalance. So in physical terms, this means that the system, there's kind of like accessible energy there. So, and I can take this energy out. So, and in a system that is in equilibrium, this is not the case. So that's kind of decayed to a state where everything is so well mixed that I cannot take the energy out anymore. So we are usually looking at these type of systems. I mean, if you do a simulation, you have this equilibration phase, right, where you want that the water particles and everything is kind of evenly out. And once this has happened, we are in equilibrium, and since the physical system shows this behavior of microscopic reversibility, we also want our model to have the same property. Okay. If this is not the case, then we're talking about driven systems. So, for example, if you have a laser pulse that is always at some point in your water boxes making everything warm, so there's kind of an imbalance and its particles are being driven somewhere else. Okay, so now I talked about a lot of mathematics. Let's get some more pictures. Here's this Howell potential. It's also used in one of these publications, so it's rather old and we've been using it a lot. Okay, so I defined a simple dynamics, Brownian motion, so it just means there's this energy landscape. It's difficult to go uphill and easy to go downhill, and there's a little, say, like thermal motion that is kind of pushing the particle around. So imagine it's in a water box or something. Okay, and just because I'm smart, and looking at and I know this energy landscape, I made some bins. I said, okay, this is of course A, this is B, this is C, this is D. But our goal would be at the end to figure out what are the states just from looking at the little thing here, not about knowing this, right? So that would be cool. So let's just see what steps are kind of important. So I have this little transition matrix, and so this is the energy landscape. This is the probability distribution, so it means that the particle will spend a lot of time in this wells. And if you look at the transition matrix, so the chances of making a transition for all of these states going somewhere else, then depending on the time that I wait, what we call the lag time, so after, say, 200 seconds, where will I end up? Just go back and restart the system. Then you see that in the very beginning, I mean, very really short time steps, because of my dynamics, it's very difficult to move very far. It's almost a line. You don't see anything. So if I'm here, I can only go here. But if I increase the lag time, then at some point you realize that, okay, it's very easy for any state in here to jump to any other. Right? So if I'm in this part, it's easy to jump anywhere. If I'm here, and jump to anywhere. So it doesn't matter where I'm in this region. I will always, like after a step of 200 frames, I will end up more or less in the equilibrium or the local equilibrium distribution in this way. Okay? And this is true for all of the states. So if I'm anywhere in this state, I will most likely end up anywhere in this state. And then if you would be able to look at this picture in full, then if you choose the right lag time, you could directly just look at the blocks and you have your metastable states. Right? So now increase the lag time even further, and you realize that at some point, one of these barriers, especially this one, is not high enough to really distinguish the states. So if I'm looking after 1,000 steps, if I'm here, it's also very likely just to end up in this state and vice versa. So by increasing the lag time, I'm more and more, in a way, getting rid of the lower barriers, right? So if you increase it even more, then you have two states. So your kind of concept of what means metastable depends on the time lengths you're looking at your system. Right? So if you're increasing this time more and more. And at some point, there's just one state. And this is effectively, so you're seeing the station distribution here. It doesn't matter where you start, after 50,000 steps, you will always jump to a point in your distribution weighted with the stationary distribution, or the equilibrium probability. So you will if you're anywhere, most likely end up in this state, a little less likely in this state, maybe this state, and so on. So, just that the picture is correct, if you would have this matrix and you wanted to compute the station distribution, what you could do is just say, okay, take this to the power of, I don't know, 100,000, and just look at one row of your transition matrix and you see the stationary distribution. It's a little stupid to, multiply a matrix a lot of time. Usually you do this by just computing the first eigenvector. So what does that mean? I said that this transition matrix, depending on tau, has certain properties. Quickly going back to this picture. So there are lots of blocks in there depending on this lag time tau. So let's first look at the property of this transition operator, which is the eigenvalues. So you look at the propagator, and you can always, if you're talking about the propagator, you can always talk about the transition matrix too. It's just, this is the continuous version, but the same thing applies for the transition matrix. So if you increase the lag time, then you see that the eigenvalues will kind of drop to zero, of course, because, why is that so? Because of this Chapman-Kolmogorov group property. To say that if I take the power of this p, it essentially means that the lag time will exponentiate the eigenvalues. So if I increase the lag time, then when you compute the eigenvalues of your Markov state model for different taus, then you see that if it's really a Markov state model, these drop exponentially. It's not, as we usually do the log scale, it's just from 0 to 1, because I wanted to show that these really go to 0. So it means there are certain regions of lag times where you only have a certain number of eigenvalues being non-zero. So if you look at the very short one, then they are all high. If you go to like 50,000, if you remember here somewhere, it's here, then we're in the region where there's only the stationary process, so there's no dynamics anymore. Here there were only 2 states, 3 states, 4 states, and then there are like, I don't know, millions of states. Okay, so that's that. So we can, in a way, say by looking at the eigenvalues, for a certain lag time, figure out how much metastable states are there, in a way. So just to make sure what the what the implied timescale is, if you compute, the timescale is just if you have the lag time divided by the logarithm of lambda I. So in a way, you're asking the question, when does the eigenvalue, at what time does it drop to 1 over e? So when does it halve? So the half-life of the eigenvalue. And for this particular model, these are the numbers. So the stationary process never decays, so it's infinite. And so these are the numbers. Okay, so what is then metastability? So if I have an idea about what lag time I'm interested in, so what region, then I'm saying that everything that is kind of still non-zero corresponds to something like metastability. Or another way, I'm saying, given a certain tau minimum, it means that there are only a finite number of eigenvalues which are essentially non-zero left. That means that this number corresponds to the number of metastable states. Okay, I realize I need to speed up a little, so keep asking questions. Okay, just to complete this picture, these were the figures that I've shown you before, and these correspond to these regions. So, and since the eigenvectors allow you to, you can express your whole matrix with the eigenvectors, it's very likely that the eigenvectors that belong to these states have something to do with this, of course. So let's look at these. And these are the eigenfunctions of the propagator. So the first one, which is for the eigenvalue of 1, timescale infinite, corresponds to the station distribution. The second one, as you see, kind of corresponds to this picture. We're saying moving from here to here. This one corresponds to this picture, and this one corresponds to adding, like going from here to here. So by just adding more and more eigenvectors, I'm adding more and more dynamics. Right? So this is just the stationary thing. If I add this one, then it's possible to differentiate these two. If I'm adding this to the matrix, I have these states and so on. So just by looking at the sign structure of these things, so where does this eigenvector go from positive to negative, indicates something about where are the metastable states located. Okay, this is what I just said. So everything that is true for continuous models also, of course, true for a discrete model. It's just the question, how do you get from the continuous to the finite model? So this is what I said. Sorry, Markov state model. This was the trajectory from before, and yeah, you're just jumping and you see that it's in these regions. Yeah, very trivial. And so we're looking at this box, that's kind of what's interesting. So if we would have this discretization of states, then you could just count. How many times is it in A and then jumps to A? How many times is it in A and then jumps to B, and so on? Just making this this table. And at the end, I can write down, okay, what's now the likelihood if I would know a certain model? Okay, let me quickly be sure that this is clear. So this is just from counting, right? Looked at the trajectory. These are the numbers that come out of it. Now what I want to do, I want to figure out what's a good Markov state model. So I want to figure out what are good probabilities that would correspond to this model. So what I can say is, well, I mean, I've seen a certain observation, and the total probability that if I have a Markov state model, this, what I've seen, would be the outcome, but just say, okay, if my Markov state model has like a 30% chance to make the transition from A to B, and I've seen A to B like 30 times, so just multiply this probability 30 times. I've seen the transition from A to C like only 2 times, I'd multiply it with the probability that this would happen. So I'm making a very, very long list. Multiply the probability to go from the position in K minus 1 to go to position K. So this is a very, very long product. And since we only have like 16 possibilities, which occur very, very long time, we say, okay, D to A didn't occur, so this one drops out. D to C occurred 115 times, so I'm saying the probability to go from D to C to the power of 115 and so on. But instead of having this 200,000 products. Okay, and then what I did is that if I would have a Markov state model, I can write down what's the probability that this would be observed. Now, the question to answer is, okay, among all possible picks of probabilities, I choose that probability that will give me the highest probability that this will be observed. It's kind of the opposite direction but it's very easy to write down. So if I would know my model, I can tell you if that would be the outcome or not. But it's still difficult, and I come to this, if I have an observation to say which is the best model. That's kind of the opposite direction. Okay, so I have a function that I can write down and it gives me a number. Now the question is, how do I get the one that is the best? So the easiest thing would be to say, okay, probabilities to go anywhere from one state needs to add up to 1, and I want a model that just has the highest probability. Yeah? So this very long product, and I want to figure out which piece do I have to choose so that thing becomes as big as possible. And if you solve this, then, I mean, you've probably seen that yesterday, the solution is just take the counts of one element and divide it by the sum of the row. So you take the sum of these. I mean, I made it so that it's always 10,000 in this example. So this would be 0.9963 and this would be 0.0037. And this is the most likely Markov transition probabilities that will be able to reproduce this. And if you think that's kind of obvious, and then actually it is. So it's exactly what you intuitively would be. If out of 10 times, 3 times I jump from A to B and 7 times I stay in A, then the chances to jump from A to B should be 30%. That's exactly what comes out of this idea. Explained a little bit complicated, but of course there's a reason for this. So what we want is we want to be able to write down a probability and say the model that we want is the most likely. And everything in a way is consistent. So this gives exactly the numbers that you would probably assume. Okay, back to the big problem of Markov state models. And this is, if you take anything from this talk, then the next slide will be the most important one, I would say. The problem is that the original timescale in the full model were these numbers, and the one from our best model that I just said were these numbers. And they're off by a factor of 10. Okay? So in a way, Markov state models, if you just do it blindly, although I actually I was able to look at the energy landscape and pick the states A, B, C, and D myself, and it looked really optimal, right? So this didn't look to be a better way to look for the metastable parts. And the best I can do was to get off by a factor of 10. Okay? And this is what we call the projection error. And one nice thing is, this is also connected to the variational principle yesterday, is that these timescales, they're always too small. They're never too big. Unless you have finite data, which you always have. So this is, so mathematically, you can prove that these numbers are always smaller than these ones. So that means you can wiggle around with your models and try to get these numbers as big as possible because they're always too small. You just pick the one which are the biggest. So usually higher implied timescales are better. Only problem is if your input data for this estimation is not, if you don't have too many data or not enough, then your statistical error will fluctuate so much that this thing doesn't hold anymore. So it's it helps a lot to know that usually you're too small, but you need to be aware if you have too little data that this can go wrong, this assumption. Okay, so just to make this a little more complicated, in this case we're just generating a model which is not reversible necessarily, because this wasn't constrained, and in most cases this doesn't happen. You would have to add an additional constraint and then do the same game again. So you say this is also supposed to be true, and then find the most likely model. And this is what PyEMMA can do for you. This is much more complicated because there's no analytical solution, so you need to have an iterative process that tries to maximize this solution. Frank has a nice paper about an algorithm that kind of samples transition metrics that are actually reversible so that you can make other things. So PyEMMA does all of this for you if you want the model to be reversible. Okay, so what can help? If you increase the lag time, then this usually makes it better. So now I'm constructing a Markov state model at like time tau equals 100 and not just 1. Then let's see what happens. So I get different numbers here, of course, because now I have different transition probabilities. And if it would really be a Markov state model, then everything should be consistent. So actually for both of the models, the original and the timescales should be the same. But in this case, they're not. But they're much closer to the original ones. So it means that if you increase your lag time usually, then your timescales are getting better. And this is if you do the implied timescale plots. You just plot these numbers with respect to tau, then you see that they are kind of increasing, and these are these plots that you have. So in a way, you're saying when the tau is large enough and this doesn't change a lot, you're sure enough that you're close enough to these ones. So this is kind of the concept behind the implied timescale. Okay, let's very quickly look at this behavior. So if you have a good projection, that's the one that I chose. So I'm saying I'm projecting on A, B, C, D in the kind of best possible way. Then I'm looking, so I know the eigenvectors of the full model, and I can compute the eigenvectors of the Markov state model. Then you see that if I expand the numbers from the Markov state model, which are just 4 numbers, right? If I have a 4x4 matrix, then the eigenvectors have 4 numbers. Then, and I say, okay, because this was the state that I projected on, so this number should be the same for all of the states. Then you see what I'm effectively doing is I'm projecting on like constant function on this on the state set that I'm doing. And very nicely, the eigenvectors look very much like the original ones, so it seems like a good approximation. And there's actually a theorem that shows that if these two things, so the one of your projection and the original one are very close, then the error is small. So this is what you want to have. Just saying here, so the relative error with respect to the lag time is kind of decreasing. Just for comparison, these dashed lines are actually something that are using OOMs. So we're just seeing that OOMs performing much better. And if you're really close, you'll see that the OOMs, once you reach this white region, where you only have a finite number of states, disappears. So you see that the relative error goes to 0 in this region where you have real metastability. So this is kind of the new thing. And if you're really interested in this, you should talk to Felix. He probably can tell you much more about this. So in a way, this promise with the projection, for Markov state models, they're always there. For OOMs, they're only there until the lag time tau is so long that you're in the metastable region, which I kind of marked here. Just for comparison, a bad projection, so I really did a bad job, and I picked the kind of the cluster centers in a way so that I'm really kind of cutting off the barriers. Then the approximation of the eigenvectors is really bad because it's kind of an average, right? So this is really awful. So the difference is, right, and you see that the relative error, I mean, even almost for the station distribution doesn't disappear. So this is really, really bad. You never really reach the exact values. As I said, yeah, so for the OOMs, this is, I mean, it's still disabled even for this, say, rather stupid projection. It gives you the correct numbers. Okay, I have 10 minutes left. So, what is the big problem in all of this is that usually, if we build a Markov state model, we have no access to the full model, but we're always working on projection. So the first steps that you made yesterday were to make like a fine discretization of your state space, right? Which is already doing this type of discretization. I mean, you're making, in a way, really fine discretization of this thing. So wherever you choose the approximation of this eigenvector, it's hopefully still be very good. But if you're in a very high dimensional space and you only have a finite number of these cluster centers, then so you only have a finite number of these constant functions to express your eigenvectors, then I mean you're kind of hoping that you placed all of these in a way that it's possible to to express the dominant eigenvectors in a good way. And this is kind of the little game that you have to hope that it works. So it's good if you have lots of states and a lot of data to really cover big parts. And I guess you'll still learn a little bit more about how to circumvent this problem. I'm not saying that you can't go around it, but you should be aware of the problem that if you're doing something wrong, you will always get a Markov state model, but you can get a very bad one, and you don't realize it. Okay? So this method, it will always give you transition matrix with numbers, but it could be that they're totally meaningless. And there are often publications for people that didn't realize this, and they're making, and it's very interesting because this is going from here to here, and so, but the model that they were using were not, I mean, it wasn't converged, or the timescales that they're using were like picked at the lag time, which was way too small. So, yeah.
So how do we know that the model is bad?
There's one of those things, I'll come to that in 2 slides or so, the Chapman Kolmogorov test. You do make some kind of consistency tests. And in a way it's, I mean, if you're doing everything and everything seems to be kind of consistent, then that's usually a hint that it's very good. With all of these sampling techniques, there's always the problem that you don't know what to do if you have not enough data. So things that you haven't seen in your simulation, there's no way to say anything about it. But it's usually very good practice to really collect lots of data, and I think that Simon will probably say something about this, that in our experience you really should have lots of data that you want to analyze. And yeah, then building your Markov model. So I would say try to use our best practices because we have lots of experience, and this is kind of what the course is about, to teach you, okay, what is a good number of microstates to choose, what is a good, if you look at the implied timescale plots, what is a good way to choose the lag time and so on. Then you should be on the safe side. Okay, let me quickly wrap this up. So this is the, it just says something about the error between, so this is the exact model. So I'm using the full propagator, and at the end I'm using the exclusive projection, and look how is it behaving on the ABCD substate. In this example, I would, after every time step, I would use the projection. So this is kind of an expression of the projected dynamics, and so it says how does my model perform. And one of the things that you realize here is that, I mean, this part is related to the eigenvectors. So if these are kind of close, then this thing is small, and if you increase the lag time, then this thing will also be small. So it kind of means that the error can be bound, although this bound is not really meaningful. The main point is that if you increase the lag time k, or if you make sure that the projection of the eigenvectors is good, then you will have a good Markov model. And all of this, what we're doing with Tika, is mainly the idea to have a projection that this thing will be good. Okay, so you're trying to find variables and coordinates on that you project so that the representation of the dominant eigenvectors will be good. Okay, so how does it look like? So I'm computing from my data for different lag time taus, what is the chance if I start in a certain state to end up in another state? And then I say, okay, just statistically, depending on how many states I had, what is the chances to have an outcome at a certain probability? So if I started at 100% at this state, then of course this will decay to the stationary probability of the state. And since when I increase the lag time, the number of samples available decreases, so the error bars increase also. So the black points would be the reality, what I want to match, and the other parts would be predicted from my model. And then it turns out, okay, if I use the Markov state model that was parameterized at 2,000 time steps to here, then you realize that you're matching these quite well. So this is kind of answering your question a little that if you look at this plot and you say, okay, for an MSM for tau equals 2,000, I'm reproducing the thing that I've seen in my trajectory because points are very well within the limits. So if you choose the lag time too small, then you see that this is kind of very off in these regions. At the end, all of these agree because everything kind of converges to the station distributions. That doesn't help it. In this intermediate region, yeah, so this is very important. Okay, I just want to mention these steps. So how do you usually do that? So you construct large transition metrics by making a very fine discretization. We talked about this using k-means or some other way to get a large. Then you analyze the eigenvectors, estimate the number of metastable states. Then you're using something like PCCA, so you look at the eigenvector structure and realize, okay, these were kind of similar, so there's a state, there's a state, there's a state. Then you're using that to construct a new projection, so you say that the regions where these are similar are the metastable states. You get to a little Markov state model, and then you compare if it's kind of consistent what you did. So that's kind of the basic outline to get to the Markov state model. And all the other things that you learn are mostly to make this really work out, so that the projection of the eigenvectors is good, and yeah, at the end you end up with the Markov state model that is useful. I realize I don't have too much time and talk too much about other things, so I will skip the Bayesian stuff a little bit. If you're interested, you can ask me later and have a look. This is just very briefly. I said that usually in the beginning you say I have an observation, and if I would have a Markov state model, I can tell you how good it is to reproduce the observation. And if you want to do the other thing, so the other way around, if you want to really predict, given some observation, what is the chance that a certain model is good, then you need to flip these kind of conditions. And the theory behind it is called Bayesian statistics. So, say this is the probability that if I have a Markov state model, I see something, and this is the probability that if I see something, I have a certain model. Then it turns out that they are very closely related, and but it needs an additional factor. This is kind of where you can input your knowledge about the system. So just want to mention that that's possible. And PyEMMA can do all of this stuff for you, actually. Very briefly about what you can at the end do with it. You probably have seen some of the stuff. You can compute relaxation timescales or eigenvalues. You can look at the dominant processes, station distribution. You can look for metastable sets, correlation functions, mean first passage times, and path probabilities. That will be covered by, I think, Fabian. Is that correct?
No.
Okay. Very nicely, because then you're talking about classification of paths, which is very closely related to OOM. So if you're really into this kind of path probability stuff, then this is the way you should look. You can also ask me or Felix about this. Yeah, this is kind of what I mentioned with the sign structure of the PCCA. It's just a little bit more elaborate if you're interested. Yeah, I'm almost done. One thing to mention for the people that are interested in this kind of clustering techniques like PCCA, there's a very nice tutorial from Uta Luxburg. The tutorial on spectral clustering, I found this very, very helpful. It explains the connection between, let's say, a graph picture, our, say, particle jumping picture between states, and the variational principle. So how all of these mathematical regions explain the same thing. So how do you express clustering with these? It also mentions briefly what compute maps are. So this is where I have this for the first time. Okay, just an example of what you can do. This is, I mean, you can make predictions for experiments. You can compute pathways. This is related to this DPT stuff. It's just kind of for. So this is the summary. So if I wrap this up, Markov state models are very, very powerful because they're extremely mathematically simple. They're very easy to compute. So these learning algorithms, I mean, are almost trivial. You just look at the probabilities that something will happen and you get your transition probability. You can compute almost anything that is kind of of interest. What's the chances that the protein will take this path and not this path. What's the chance to go from here to here and so on. The only thing that you should really be concerned about is that whatever you do, you will always get a Markov state model, but you need to make sure that it's a good one. And the thing that can often go wrong is that you're kind of projecting in a way badly, and then I mentioned that. Just keep in mind that just because you get a Markov state model, it doesn't mean that it's good, so make sure that it's a good one. Feel free to ask anyone, we have lots of insight and helpful tips.